Hello everyone, myself Mayur Patil, and now I am here to present PPT on shear stresses in adhesive joints of composite structures. So, introduction. So, what are the adhesive joints? Joints used for composite material like fibers, laminates, metals, and advantages over mechanical fasteners, lightweight, no stress concentrations, unlike bolts, rivets, smooth load transfers. And what are their applications? Applications like aerospace, automotive, wind turbine blades, supports equipments. So, and basic adhesive joints. So, what are the types of adhesive joints? Single lap joint, double lap joint, so scrap joint, bird joint. So, here we can see that single lap joint like this, double lap joint, butt straps, double butt straps, here butt, tabular lap. These kind of joints so load transfer mainly through shear stresses in adhesive layers. So stresses distribution in adhesive layer. So adhesive layer is very thin, is nearly equal to zero point 0.1 to 0.5 mm. Stresses varies along overlap length due to load transfer mechanism, stiffness, mismatch of adherents, peak stresses occurs at end of the overlap. So here we can see one graph is there. So it varies along y-axis, that is maximum shear stresses, and along x-axis overlap length. So here we can see graph how the graph is changed along the length and along when shear stresses are increased. So governing equations. So here we are seeing the equation for shear stresses in adhesive layer, that is tau x p by bt in bracket cos h bx beta x upon sin h beta by L by 2, where P is the load, B is the width of joint, T is the adhesive thickness, L is the overlap length, and beta is the 2GA upon ET, stresses parameter. It is the stress parameter constant. So here we can see tau is the shear stresses. From this equation, we can calculate uh, shear stresses in adhesive layers, or we can calculate load acting or overlap length when we know other values. So derivation, it is a little bit simple derivation, simplified derivations. So for that we have to assume that linear elastic adhesive, perfect bonding, small deformation, differential equation. What is the differential equation? We are seeing here d squared tau upon dx square minus beta square tau equals to 0. So solution is uh, hyperbolic function of x as shown in previous slide. Like this is explains stresses concentration at edges. So here this is edge. At the edge, which kind of load means how much load is acting we can find. So it is one of the example we can solve by using that previous formula which we are seeing in previous slide, like single. So now see what is the example is given. Single lap joint example. It is the single lap joint example given. Load is equals to, means P is given, that is 5 kilonewton, width is equals to B is equals to 25 mm, thickness T is equals to 0.3 mm, overlap length is also given, which is 50 mm, and adhesive shear modulus, that is GA, is also given, that is 1.2 GPa, gigapascal. And they said to calculate maximum shear stresses. So from this formula, we can calculate maximum shear stresses. That is tau max is equals to P by Bt into f of b in b comma L. So factor affecting shear stresses: adhesive thickness, too thick, weak, too thin, brittle, overlap length, optimum required, and a material mismatch, different moduli of the adherence, temperature and environments, moisture, heat. So various factors are affect shear stresses like adhesive thickness, overlap length, material mismatch, temperature and environment. So failure, which kind of failure we are seeing in adhesive joints? So first one is adhesive failure, then next one is cohesive failure, then substrate failure. So in adhesive failure, separation at interface means two parts are separated. So cohesive failure, failure within adhesive layer. So the incohesive failure between these two metal parts, adhesive is there. So in this layer of adhesive, failure is occurs. Substrate failure, composite itself breaks. So this composite itself breaks. So due to that, substrate failure is comes, stresses concentration initiates and overlaps ends. So this kind of failure can come in adhesive joints. So conclusion, adhesive joint crucial for composite structure. As we all know, adhesive joint is crucial, very crucial for composite structure. Shear stresses distribution is non-uniform, highest at overlap ends, and accurate prediction via mathematical models improve design safety. So it is also most important thing which we have to calculate mathematically by making mathematical model which can improve design safety. So applications in aerospace, automotive rely heavily on such analysis. Future. In future, use of nano adhesives improve modeling via FEA. So in future, we are shifted to nano adhesive, which can improve modeling with FEA. So that's all. Thank you. So thank you very much for giving your precious time. So that's all for today. That's thank you.